In this video, I'm going to give a proof of the intermediate value theorem, actually the first version of the intermediate value theorem. Before we actually use the first version to prove the second version, and then use the second version to prove the third version, but we have not proved the first version of the intermediate value theorem. That's why now we are going to do that, okay? So let me recall the first version of the intermediate value theorem. Let f be a continuous function defined on a closed interval AB, and suppose that f of a times f of b is less than 0. That means either f of a is less than 0 and f of b is greater than 0, or f of b is less than 0 and f of a is greater than 0. The conclusion is there is some c in the open interval AB such that f of c is equal to 0. Okay? So here, without lots of generality, we only need to consider the case where f of a is less than 0 and f of b is greater than 0. Okay? So I can say, suppose that f of a is less than 0 and f of b is greater than 0. And then we can also prove the second case in a very similar way. So let me first explain the proof by using a figure, and then I will present the formal proof. Okay? So the idea is as follows. Now here, this is f of a and this is f of a. f of a is less than 0 and f of b is greater than 0. Then this is the graph of the function f. Then this c satisfies the condition that f of c is equal to 0. The idea is as follows. We consider the set A not consists of all x in the interval AB such that the function value at x is negative. Okay? So this is the set A. In this situation, the set of all x in the interval AB such that f of x is less than or equal to 0. Okay? That means the graph is below the x-axis. Okay? So this is the set A. And then A is non-empty because it contains the point little a. Okay? As you know, f of a is less than 0, so A belongs to capital A. And the set A is bounded above. So A is non-empty and bounded above. Then the supremum of A exists as a real number by the completeness axiom. So over here we can see that the supremum of A is a real number, and we denote it by C. Okay, so C here is the sup of A. It's similar to the largest element of A, but the largest element may not exist, so we use the supremum, which has several similar properties to the largest element of a set. Okay? So because the set A is bounded above by B, C is less than or equal to B. Okay? And because C is an upper bound of the set A, and little a is in this set, C is greater than or equal to A. That means C is greater than or equal to A and less than or equal to B. Okay? So then it suffices to show that f of C is equal to 0. Then C has to be in the open interval AB because C cannot be A and C cannot be B. Why? C cannot be A because f of A is less than 0. If we can show that f of C is 0, then C cannot be A. Okay. Similarly, because f of B is greater than 0, C cannot be B. Because if we can show that f of C is equal to 0, again, C cannot be B. So our goal now is just to show that f of C is equal to 0. And we are going to accomplish that using properties of the set A, and also a very important property of the supremum involving sequences. Okay? So then by a property of the supremum here, there exists a sequence AN in the set A not converges to C. Okay? And because AN each an in this set A, f of an, as you can see here, is less than or equal to 0. And because an converts to C, f of an converts to fc by the continuity of the function f. Now, this constant, you can imagine that 0 here serves as a constant sequence 0. It converts to 0. So, by the comparison theorem, f of c is less than or equal to 0. Okay. And therefore, c cannot be b because you know that f of b is greater than 0. So, therefore, c has to be strictly less than b. Okay. c is strictly less than b. Now, because c is strictly less than b, we can always find another sequence, bn, that is in the open interval cb not converted to c. Okay, so we can find bn not converted to c, and bn is in the interval from c to b. Okay. Now, here, because bn is strictly greater than c, bn cannot be in the set A. Okay, and therefore f of bn has to be greater than or equal to 0. I'm sorry, in fact, f of bn is strictly greater than 0. Why? You can see from this figure, but you can also see by contradiction. By contradiction, suppose that f of bn, what if f of bn is less than or equal to 0? Then bn has to be in the set A, because A consists of all x in the interval AB such that f of x is less than or equal to 0. So bn has to be in the set A. And because bn is in the set A, bn has to be less than or equal to c, which is the supremum of the set A, or the least upper bound of the set A. But this is not the case because you can see here that bn is greater than c. Therefore, in fact, we have that f of bn is strictly greater than 0. Okay, so now we have that f of bn is strictly greater than 0 for all n, and f of bn converges to f of b. And again, by the comparison theorem, f of bn converges to f of c. Okay, and again by the comparison theorem, because f of bn is strictly greater than 0 for every n, f of c is greater than or equal to 0. Now we have that f of c is less than or equal to 0, and f of c is greater than or equal to 0 as well. Therefore, f of c is equal to 0, and the proof is complete. Okay, so let me recall the proof by 3 steps in the closed interval AB such that f of x is less than or equal to 0. Then A is not empty because little a is in the set A. Now here in this graph, the set A is the union of this interval and this interval. And A is bounded above by B. Why? Because every x in A is less than or equal to B. Okay. Therefore, by the completeness axiom, the supremum of A exists as a real number, and we denote it by C. Then, C is greater than or equal to A and less than or equal to B. Okay. Now, it suffices to show that f of C is equal to 0. Because when f of c is equal to 0, it cannot be A and it cannot be B. Therefore, it has to be in the open interval AB. Okay, so now our next goal is to show that f of c is equal to 0. Okay, so let me move to the second step by showing that f of c is in fact less than or equal to 0. Okay, now because C is the supremum of the set A, we can find a sequence A and in A that converges to C. So please see my video lectures on the supremum and the infimum to find out this property. By the continuity of f, because an converges to C, f of an converges to f of c as n approaches infinity. Now, because f of an is less than or equal to 0 for all n. Why? Because an is in A for every n. Okay. Then by the comparison theorem, f of c is less than or equal to 0. Okay. And because f of c is less than or equal to 0, c cannot be b. Why? Because f of b is greater than 0. Okay. So c has to be strictly less than b. Okay. Now, we are going to move to the third step by showing that in fact f of c is greater than or equal to 0. Why? We can pick a sequence Bn in the open interval Cb such that Bn converges to C as n approaches infinity. So over here, this is C and this is B. So one way to pick Bn is let Bn be C plus B minus C over n. Okay, so we can pick a sequence in this interval not converges to C. Okay. As I explained before, then f of Bn is greater than or equal to f of Bn is strictly greater than 0 for every n. If not, then f of Bn is less than or equal to 0, and so Bn has to be in the set A. So Bn is less than or equal to C. That is not the case by the way we choose Bn. Okay. So again, since f of Bn is strictly greater than 0 for all n, and f of Bn converges to f of C as n goes to infinity by the continuity, we have that f of C is greater than or equal to 0. So f of C is both greater than or equal to 0 and less than or equal to 0. As a conclusion, f of C is equal to 0 and the proof is complete.